Welcome to the 51st lecture on computational mathematics with SageMath. In this lecture, we are going to explore some methods of solving ordinary differential equations numerically or numerical solutions of ordinary differential equations. Not every differential equations can be solved analytically. So, in that case you need to appeal to numerical solutions or find some approximate solutions, similar to what we saw in case of finding root of an equation of the form fx equal to 0. In case fx equal to 0 we are unable to solve explicitly, then we try to approximate a solution by means of numerical techniques. So, for example, let us start with a differential equation dy dx is equal to e to the power minus x square into sine x cube. Now, if you try to solve this differential equation, if you in Sage using DE solve, then you will not get explicit solution. So, it simply returns the constant and integral of this right hand side, which is not what we want. So, in such situation, so this is one such example. There are several examples where you cannot solve this differential equation explicitly. Solving differential equation of this form amounts to finding integral of a function, and we have also seen that you cannot find integral of every function. Even though the function is integrable, you may not be able to find its integral. So, in that case we find numerical integrals, right. So, this is an example where Sage is unable to find a solution explicitly. So, in that case we need to appeal to numerical methods. So, the first and the simplest numerical methods we will look at is known as Euler's method. So, what is it? Suppose you want to solve this differential equation dy dx is equal to fxy, and with initial condition y0 is equal to y at 0 is equal to, let us say, some number y naught. Okay. So, the idea is to obtain or approximate value of y, which is solution of this differential equation, at some point starting with x equal to 0. Okay. So, how does it work? So, in order to find the approximate solution, an approximate solution of y at x equal to, let us say, b, what we do, we divide this interval x naught to b. X naught is the starting point at which the value of the solution is given in n equal parts, let us say x0, x1 dot 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 xn. So, length of each of this sub interval will be nothing but b minus x naught by n, and that let us call that as h, which we call as a step size. Now, let yi be y at xi, y at xi, that is what, and these y at xi except I equal to 0 is what we need to find out, and on the in the process we will be able to find y at n, y at x n, y at b, right. So, let us see how we will do. So, the basic idea behind this is to approximate the function, that is y, by a linear approximation or by a tangent line. So, it is based on the assumption that the tangent line to the integral curve, which is the solution curve at any point xi y I, approximates the integral curve over the interval xi comma xi plus 1. So, in case xi plus 1 is very close to xi, this approximation, which is linear approximation of the function y, will be reasonably good approximation. Now, since the slope of the integral curve at any point xi yi is already given to us, namely that is y dash at xi, which is f at xi yi, the equation of the tangent line in this case will be given by y is equal to f of xi plus f at xi yi into x minus xi. Now you substitute, suppose we want to evaluate at x equal to xi plus 1. So if you substitute x equal to xi plus 1, that is xi plus h, then yi plus 1 will be yi plus h times f at xi. And so what is this is so first iterate, namely y1 will be what, y1 is equal to y naught plus h times f at x naught y naught. So once we know y1, then we can find y2, and then we can find y3 and so on. In general we can find yn, right. So therefore what happens is the iteration scheme of this Euler's method, this is what is called Euler's method, is given by yi plus 1, that is y at xi plus 1 is equal to yi, that is the value of the solution, approximate value of the solution at the previous point, plus h times f at xi yi. So that is how this iteration schemes is defined, and then I can take value 0, 1 to n minus 1, right. So this is, now let us write a Python program, user defined function for Euler's method. This is fairly simple. So we want to input the value of the function f, the initial point at which the initial value is given x naught, and the value of y at x naught, the step size h, and the point at which you want to evaluate that. In this case we call that as a b. So x1 is b here. So now then define what is n. N will be the x1 minus x naught by h. Since h is given by, if you are dividing in n equal parts, h is given by b minus x naught upon n, therefore n will be given by b minus x naught by h. So here we have taken, instead of b we have taken x1, so this is what we have. Now let us define xv and yv, value of xv. xv will take value of x1, x0, x1, x2 up to xn, and xi is nothing but x0 plus h times I, that is the node. We call them as node points or nodes. So xv and yv initialized to x0 and y0, and what we are going to do, we will find the solution at all these node points, that is at every xi we will find yi. So we will put these values in a list, namely xi yi, we will create a list of xi yi. So now for I going in the range of 1 to n plus 1, because you have to go up to n plus 1 because xn is your b x1, right, and these are the initial for x equal to, for I equal to 0 it is already given, therefore we have to start from I equal to 1. And then what is xv? xv is x0 plus h times I, that is ith node point, and the value of yv is yv, that is the previous value. So in this case, for example, it will take y0 and it will find y0 plus h times f at x0 y0, and you append this xv yv to this solution, and at the end return this solution. So this program is fairly simple, very simple in fact. Now let us call this method the Euler user defined function, and let us solve an ordinary differential equation of first order, namely dy by dx is equal to x into 1 minus x square upon y into 2 minus y, with initial condition y0 is equal to 0, and let us find out value of y at node points 0.1, 0.2 up to 1. So here step size is 0.1. Okay. So let us define x and y as variables. F dy dx is equal to fxy, so this right hand side we will define as fxy, and x naught is 0, y naught is 1, h which is step size is 0.1, and the x1, the end point at which we want to find the approximate the value of y is 1. So now let us call Euler underscore method of f x naught y naught h comma x1. This gives you a list of xi yi. So if 0 at 0 it was 1, at 0.1 it is 0.9901, and so on. At 1 this is 0.748162 and so on, right. You can tabulate this value, you can put it in a tabular form using a function called table, and then you need to give this list, and then if you want the heading you give the heading. So here we are saying the headings are xi yi. So let us run this. This is what you get, xi. So I equal to 0. If you want, you could have also printed the iteration number as one first column. So this is at 0 it is 1, at 0.1 it is 0.999 and so on, right. So that is how you can find the solution, right. Now you can also use inbuilt function. In the last lecture I told you Sage already has several inbuilt functions to find numerical solution of an ordinary differential equation, and Euler underscore method, Euler's underscore method is one such. So let us call that Euler's underscore methods, that is inbuilt function of f. So you have to give input f, and then the initial x naught, the value of f y at x naught, the step length, and this is the end point, and it says that it uses an option called table. So it will tabulate the value exactly the same way as we have done in this case, right. So let us run this and then see what we get. So here by default this says reports x value, y value, and h times fxy value. So I mean this is just to see that y plus h times fxy will be the next iterate. So that is what you can see here. This was 1 and this is 0.0099, and the next value comes as 0.9901 and so on, right. So this is exactly very similar to what we have done, except that it is also reporting h times fxy at every iterate. We have already seen how to solve this kind of differential equations analytically. So if you try to solve this using DE solve, and then let us see what the solution we get. So this solution is given in terms of y and x, and this is implicitly defined. If you want to solve this explicitly, this will require again some another numerical technique, because in some cases you may be able to find y x explicitly, but in most of the cases it may not be possible. So let us look at geometrically what it means. So first let us plot the graph of the solution, and that we can do it using streamline underscore plot we have seen in the last class, and we want to plot the integral curve passing through x0 y0. That is the starting point, and then we also want to plot the set of points xi yi obtained using Euler's method, right. So we are calling T to be the Euler underscore method, and then create a table of this value. So this actually is at present is not required. Let me get rid of this, and then C1 is streamline plot, that is the solution curve, integral curve. You can think of that as explicit the curve, or the solution obtained explicitly, and the C2 to be the plot the set of points in the table T, and put a marker as a dot, and marker size is 3. So let us run this. So when you run this, this is what you see. So you can see here this blue one is the original curve, or not original curve, I would say. This is the actual solution. Blue one is the actual solution, and the red one is the approximate solution. Now in case you are going to increase the step length, suppose I decrease the step length, suppose I make it 0.05, and then you will see that the solution curve, the approximate solution curve will be much closer to the actual solution, right. So you can try with even smaller step size and then see the solution, approximate solution. Now you can also try to kind of tabulate the errors. So at every step, for each step size, let us say 0.1, 0.05, 0.025, you are approximating the value of y, right, you are approximating yx with this given step size. So there is always error. Now what we would like to do is, let us also tabulate the error at each stage, right. Now let us in the previous example we did not have the solution in explicit form. So evaluating explicit solution or exact solution will not be straightforward. Still one can do numerically, you can approximate, but we will look at an example where we have the explicit exact solution. So in this case we are looking at y dash plus 2y is equal to x cube into e to the power x by 3, and y at 0 is equal to 0, right. So let us first solve this analytically. So in this case the solution is solution of this initial value problem is 1 by 4 into x to the power 4 plus 4 into e to the power minus 3x, right. I think this there is small difference between this and this. So here I should okay, let me change this differential equation. Let us change this to 3y and this is 3x. I would have first taken that differential equation, while solving I would have changed while experimenting, right. So this is the differential equation. Its solution is given by 1 by 4 into x power 4 plus 4 and the whole thing multiplied by e to the power minus 3x, right. That is the explicit solution, right. So you can evaluate this solution at 1.0, this is what you get, this is the explicit solution. Of course right, this is the approximation of this will also be an approximate value, but in any case this will also involve some error, right. Now let us tabulate the value of xi yi at each of these node points for step length 0.1 to begin with. This is the step length, we are taking this step length to be 0.1, and then so here we have to write this differential equation as y dash is equal to fxy. So we need to push this the left hand side 3y to the right hand side. So that is why fxy is equal to minus 3y plus x cube into e to the power minus 3x, and let us store this solution using Euler's method in solution n, and then let us find the length of this, and then let us also define the error term. Error term is going to be the value of the yi minus explicit value or exact value of y at xi obtained that is stored in SOL. So SOL at xi. So that is what is done here. This is the initial error is 0. So we have xi yi. So this is x naught y naught, and the initial error is 0. And in that next time we will append solution x, the first coordinate of the solution at in and then second coordinate which is yi, and then the absolute value of the difference of the yi with the exact solution, and then also, and after that you print this using a table. So here we are xi yi and these are the error. So you can see here in this case there are quite a bit of error, in this case almost 2% error here, right. Now suppose we decrease the step size, suppose we take it 0.05 and again try to tabulate the error at each of this node point. So you will be able to see that this error is much smaller than error using 0.5. So you can see here in this case error is 0.01103, and in the previous case at 1 the error was 0.02. So almost it has become half of the previous error. And similarly, if I reduce the step size again by half and then try to tabulate the error, then you will be able to see that error would have decreased further. So again, so it is almost half of the previous error. So you can see here in this case the error seems to be reducing linearly, right. So it is not very fast method in that sense. Of course there are you can look at the theory and see what is how this error can be obtained, right. Error will be function of the step size h, and right. So you can even compare all the errors together using this very simple Sage code. So we are defining x naught y naught and x1, the error table I am just calling, so that we will print value of xi and the error for taking step size 0.1, 0.05 and 0.025, right. And so these are the nodes we are defining, initialize these errors, and then for first one let us append this error in E1, and then the second step size append this in error E2, and then similarly do it with x3, that is step size 0.025, and let us run this and let me tabulate this. So this is what you get. So you can now you can see here the error term at h equal to 0.1, h equal to 0.05 and h equal to 0.025. So you can compare the error at every stage, right. And this error we have computed only at actually node points 0.1, 0.2, 0.3 up to, I think one should go up to 0.1. So you have to say range 11 in this case, right. So now it will go up to 1, right. So that is what we saw. So you can see here the error is almost becoming half of the error in this case. So this h is half of this and this h is half of this, and error is also becoming half in this example, right. So now let us look at you can make improvement in this Euler's method in order to make the convergence faster, or in order to reduce the error. So how do we do that? This is again fairly simple. So in last time we approximated the value of y at xi by the slope, namely f at xi yi. But this time what we do is we instead of taking the slope at yi xi yi, we take the average of the slope at xi yi and the next point xi plus 1 yi plus 1. So m is half of this, and then we define the tangent at xi yi with this as slope, right. So this is the equation of the tangent at xi yi with slope m. But if you notice that this requires value of f at xi plus 1 y at I plus 1, but y at I plus 1 is not known, okay. So we know only yi. Therefore what we do is we replace this by h times f xi yi. We replace it by this, there is a comma missing here. So we replace this yi plus 1 by h f x I yi. Therefore this iteration scheme becomes yi plus 1 is equal to yi plus h by 2 into f at xi yi, which is plus f at xi plus 1 comma yi plus h f at xi yi. This is the iteration scheme for modified Euler's method or improved Euler's method. So let us implement this. Again let us write a Sage routine for this. This is exactly similar to the previous one, except that here this computation of yi has changed using this formula, right. So let us run this, and then let us use this to solve this particular differential equation. This is the exactly the same as the previous one. So again I should change this to 3y and here to minus 3x. So that is the differential equation. In the previous case also I had made the appropriate change. Okay, this was actually minus 3x. It should be minus 3x. Yeah, right. So let us come back to this next example. So we want to solve the same differential equation using modified Euler's method, so that we can just compare the two solutions. So again this is the analytic solution which we have already obtained. Now let us define f of x y is equal to minus 3y plus x cube into e to power minus 3x, and then call this modified Euler's method. So this is again giving you xi yi, and let us find out value of f at the actual exact value of the solution at x equal to 1 is this 0.622, and here also 0.61. So it is actually matching up to 2 decimal places, right. And now let us tabulate this along with the error. So exactly similar to this, except that we are calling modified Euler's method. So let us tabulate the xi yi with error. So you can see this error, if you compare this error with the Euler's method, it will be much smaller, right, it will be much smaller. And in fact even if you see here, it is less than half actually. Yeah. So now you can compare this all these the two methods, so with the same function, and let us try to tabulate T1 as the solution using Euler's method and T2 using modified Euler's method, and let us tabulate these two together and then plot the two graphs. So here this blue one is the exact solution, the red one is solution obtained using modified Euler's method, and the green one solution obtained using Euler's method. So you can see here the green one is quite far away from the red this blue one. So the error in case of Euler's method is much more. However, if you kind of reduce this, let me make it 0.05, and then try to let me make the figure size small, show this, and fig size is equal to, let us say, 4. Yeah. So now you will see they are much closer to each other, but still this Euler's method has lot more error, right. So you can explore more examples and try to you can also tabulate error using Euler's method and errors using modified Euler's method. So it will also show you that the error in case of modified Euler's method is much smaller, right. Let me leave you with some few simple exercises. These are all exercises to solve this numerically using Euler's method and modified Euler's method. So you use both of them and also tabulate the value yi xi yi and try to also plot its graph. So in different and take the different step size, right. So that is the simple exercise. Let me stop here. Next time we will look at another method which is known as RK4 method.